Welcome to qnawire.
As a number of parts, we are first asked to compute this integral involving the variable k for the function b sub k indicated. This will allow us to find a wave function. We're asked to graph this wave function in x and also the function b of k versus k for two situations when k naught's 2 pi over l and when n pi over l, where l is some characteristic length. We're then asked to estimate a width in a real space using two minima in psi. We're then asked to do the same for a momentum space where this width is defined as h over 2 pi omega sub k. And we're asked to calculate this product and give some comment. So let's start by doing this integral. So because k is defined in a restrictive way, if it's 0 beyond k naught, we don't have to actually integrate to infinity. We can integrate to k naught. Oh, we're solving this an integral to find psi of x. So our b of k comes out to be simply 1 over k naught as defined in this region, multiplied by cosine kx dk. And it's worth noting we're not integrating in x, we're integrating in k, so you have to be super careful about treating x as a constant in this situation. So when we do that, we are left with 1 over k naught times 1 over x, because that's the constant that we're pulling out in k. Kx evaluated from 0 to k naught, which will leave us with 1 over k naught x sine of k naught x. And that's our psi of x. So this looks like a sort of sinc function. It's decaying. Yeah, we could take a look at it here. If we plot it in x, we can be doing something like this. And symmetric, it's anti-symmetric rather on both sides. So that could have been drawn better, but you get the idea. It's a sine, but it's decaying over the course of x. So if we were to identify this width on both sides of a maximum zone, this would probably be the best one to choose. So the first of these mins occurs at x equals 0. The other one occurs when this whatever's inside the sine function. So when sine of k naught x is equal to 0 the first time, which is true when k naught x is equal to pi over 4 is equal to pi. Thus when x is pi over k naught. So this width between x equals 0 and x equals pi over k naught, these 2 points right there, this width would be pi over 2 pi over L, or we can leave it that way. It's just going to be pi over k naught. So when k naught is 2 pi over L, we have the case that omega x is L over 2. And when k naught is pi over L, in that second case, we have omega x being just simply L. Okay, so that's straightforward enough. Oh, and we were also asked to plot bk versus k. It's just some step function, just goes to the edge, falls off at k naught to 0, and it's 0 on both sides. And when it's at it's just k naught up to the k naught threshold, falls off to 0, and that's it. Nothing too special there. Okay. So we're then asked to find this product, omega p times omega x. These are widths in momentum space and real space. So that's how I'm doing it, which is h omega k over 2 pi omega x. Omega k I'm interpreting as the width in k space of that bk function. So I think that's just k naught. And omega x, as we defined, is pi over k naught. So we got some cancellation that will occur. And we're left with just h over 2. So I think the main point of this, the result here, is that the width is that you can think of these widths in both space, in momentum space and position space, as like an uncertainty. So this is very analogous to delta p, delta x greater than or equal to h bar, for example. This is like a Heisenberg uncertainty principle. The product of these two widths is equal to some value that doesn't depend on any other variables. So it's in other words a constant. So you can only vary one or the other, and the other one will change, have an opposite effect. So I think that's what this problem is getting at, although it's a little bit convoluted. But I think we got to the end. We got everything we needed. And that's it. Thanks.